use neutron to bombard nuclei to study beta decay. So everybody know aneuploidy, and many people actually work in Los Alamos. One of the target was to produce the atomic bomb, and they are successful. Bom itu juga yang digunakan untuk Hiroshima dan Nagasaki. Aneuploidy adalah antara orang yang utama yang memainkan peranan dalam penciptaan bom ini, termasuk juga several other names lah yang terlibat dengan projek itu. But Aneuploidy was given the Nobel Prize in 1938 for the study of the beta decay. Okay. But Meitner and Frisch Aneuploidy 1935 onwards. Meitner and Frisch dia bernasib baik because they use neutron to bombard on uranium. So this is the first and found that there are splitting of this uranium into half. So this is the first study producing fission. So for this work they were given a Nobel Prize. And then, of course, Fermi developed the first nuclear reactor at the University of Chicago based on chain reaction. Fission chain reaction. Okay. So that is the so Aneuploidy actually work on the atomic bomb and also the nuclear reactor. But he did not get any Nobel Prize for developing the nuclear bomb or the nuclear reactor. He only got the Nobel Prize for beta decay, studies on beta decay. Okay. And even though fission was discovered by Meitner and Frisch, Aneuploidy, who is the one who developed the nuclear reactor. So all nuclear reactor now pahala dia dapat pada Aneuploidy. Okay. So you should baca apa ni? Biografi Aneuploidy. Saya pernah membaca tapi saya tak ingat siapa penulis dia. Very interesting how he traveled from University of Chicago, di mana dia mengajar, Dengan dia buat eksperimen, dia travel to Los Alamos dalam train. Dan dalam train itulah dia buat all the calculation. Kita kalau dalam train tidur, kalau tak tidur pun tengok apa ni, Facebook lah, apa dan sebagainya. Okay. Tapi Enrico Fermi produce a lot of his major work during the traveling in the train. So he's a very great man, Now, let us use this sketch of the binding energy to make an estimate. So we start with uranium-238. An estimate. Say, using uranium-238. We all know that heavy nucleus somewhere here. Heavy nucleus, okay? Light nucleus somewhere there. Katakan ni. So heavy nucleus. So U238, suppose it's split into two. That is A equal to 119 plus A equal to 119. Split into two. Spontaneously, suppose. Here the binding energy is about 7.6 per nucleon, whereas here, because it is less A value is about 8.5. This is MeV. Okay? 8.5 MeV per nucleon. Okay. So that the higher one less and the lesser one higher binding energy per nucleon. You know that you have energy change. You have minus 238 times 7.6. This gives you minus 1809 MeV. Why minus? Because binding ni negative. Your repulsive positive. So this is binding energy change. Now, this 119 jatuh pada palladium Pd. Palladium 119. Split into two palladium, katakan. Then it will be, there are two of this palladium time 119 time 8.5. So what do you get? Minus 2033 MeV. Okay. So there is a difference of 214 MeV. What does that tell you? In the first place, why does uranium-238 exist? It has lower binding energy than 2 palladium. Lower binding energy. So the lower energy state are preferred. So try to relate this with this energy here. and the separation. Suppose this is the what you call it, the binding, the total energy of this uranium-238. So this uranium-238, better put 2 like this. Actually, uranium-238 is 2 palladium like this. Dia sebetulnya, kalau menjadi, maknanya dia adalah itulah. Actually, this is the 2 palladium is actually like this here, and this 214 is kinetic energy of U238 or 2 palladium. So that extra energy here actually become its kinetic energy. Okay? Sebab apa? These are static energy. So the difference must go to the kinetic energy. Okay? So this is the kinetic energy. Bila kinetic energy dia tidak zero di sini, okay, it become something positive. But you see, if you calculate the Coulomb barrier, the Coulomb energy, now you need to calculate and find what is the height. Is it higher or lower than this kinetic energy? This is very important. You know that what you call it, Coulomb energy is given by 1/4 pi E0 Z1 Z2 E squared divided by R. And now this Z1 is equal to Z2 because there are 2 palladium. So R1 equal to R2 because both are palladium, and this is 1.25 A to the 1/3. You know this formula, and that is 1.25 times 119 to the 1/3. That is equal to 6.1 times 10 minus 15 meter of FM. So this is 6.1 femtometer. Sometimes called the Fermi. 10 minus 15 ni sometimes called femtometer, sometimes called Fermi. So sama lah dia punya short form FM. So bila kita masukkan dalam formula ni, Z1 Z2 is 119 119. Okay? So Coulomb energy become all this factor is 1.44 MeV FM. Okay. That constant, and then you have now out of that 119, Z is only the number of proton. The number of proton is 46. Tak banyak, dia kaya neutron, palladium ni. Ya, bila-bila berat, semuanya kaya neutron. So it only has a 46 Z value. And then this R is obviously, kalau kita assume dia begini, so R1 equal to R2. Okay, the radius when they got sort of combined. So that will be 2 times 6.1 Fm. So since this is Fm, this is Fm, so you'll get something in MeV, which is roughly about 250 MeV. So that is 250 MeV, and the kinetic energy is 214 MeV. So that's the reason why the uranium-238 doesn't split. Sebab apa? Coulomb energy pegang dia. Dia nak berpisah tapi tak. Bahasa orang tu hampir berpisah tapi tak berpisah. Sebab dia punya Coulomb punya daya tarikan Coulomb kuat. So melebihi. So this led to the idea that of what you call activation energy. Activation energy adalah the energy that is required to overcome the Coulomb barrier. Okay? To overcome. Dia slightly below, lepas tu dia nak overcome barrier supaya dia berpisah dua ni lah, palladium. So that is called the activation energy. That is the energy required to fission by overcoming Coulomb barrier. But this fission, what do I mean by fission? These are the so-called spontaneous. Why? Sebab dia dengan sendirinya, saya tak excite dia pun. Nanti kita akan bincang apabila we use so-called induced fission. Bila menyerap neutron, dia excited, dia berpisah. So that's induced fission. This is spontaneous. This is for spontaneous fission. Okay? Induced fission kita cerita sekejap lagi. Now, so there is another approach where we can estimate when this spontaneous fission happen. We can estimate when spontaneous fission occur by just studying shape change.